In the world of heavy industry, you're constantly fighting against physics to move fluids under just incredible pressure. And there's one machine that's an absolute master at this, but it has a violent, dangerous secret. So today, let's dive into the powerful world of reciprocating pumps and the amazing engineering it takes to tame their destructive pulse.
All right, so picture the heart of industry. We're talking oil refineries, massive chemical plants. In places like these, moving fluids isn't just a simple task. It requires immense, almost unbelievable force. This is a high-stakes environment, and it demands some seriously powerful and specialized equipment to handle that kind of extreme pressure.
And this is our hero, the reciprocating pump. Now, it's what's known as a positive displacement pump. That just means it traps a very specific amount of fluid and then literally forces or displaces that fluid out. It doesn't spin like a fan or a propeller. Instead, it uses a piston or a plunger that moves back and forth, that's the reciprocating part, to shove that precise volume of fluid forward with every single stroke.
And this visual just perfectly shows what's going on. On the left, you see all the complex engineering, but on the right, you see the simple principle behind it all. The core action is just this. As that plunger pushes forward, it forces the fluid out under tremendous pressure. It's this direct, powerful, brute force action that really sets these pumps apart.
So, you might be asking, why go through all this complexity? Well, it's because these pumps can do things that other pumps just can't. They can generate enormous pressures. We're talking over 3,000 psi. And unlike pumps that spin, they're super efficient at moving thick, gooey, viscous fluids, like crude oil. Plus, since every single stroke moves a precise fixed amount of liquid, they are perfect for what's called metering, where you need to inject exact chemical doses. But all that power, it comes at a price. The very nature of this start, stop, push-pull motion creates a violent, rhythmic pulse throughout the entire system. You can almost say the machine is, by its very design, built to shake.
And we're not talking about a minor little vibration here. These pressure waves, these pulsations, they don't just stay at the pump. Oh no, they travel down the entire length of the piping, shaking everything they're connected to. It's kind of like hitting one end of a long metal pipe with a hammer and feeling that shockwave travel all the way to the other end.
And this constant shaking leads to some really severe problems. It causes mechanical fatigue, which basically just weakens the metal over time until it breaks. It can cause something nasty called cavitation. That's where tiny vapor bubbles form in the liquid and then violently collapse with the force of little explosions. All of this, plus just intense, deafening noise, can ultimately lead to catastrophic equipment failures. The stakes here are incredibly high.
So how in the world do you fight back against that? Well, the first line of defense is a pretty clever device that's designed to act like a shock absorber for the whole system. Let's take a look at how they cushion that violent pulse.
This little guy is a pulsation dampener. Think of it as a super sophisticated shock absorber for the pipeline. Inside, there's a flexible diaphragm or bladder, and it's charged up with nitrogen gas. It sits there in the pipeline, perfectly positioned to absorb the pressure punches that the pump is throwing out.
So here's the magic. When the pump shoves a blast of fluid forward, creating a huge pressure spike, that gas inside the dampener gets compressed, and it absorbs that energy. Then, in that little lull between pump strokes when the pressure dips, the compressed gas expands and pushes that stored fluid back into the line. The effect is that it turns this violent series of pulses into a much smoother, much steadier, and much safer flow.
But, dampeners aren't a silver bullet. There's a much more subtle, more insidious danger lurking in the system. It's one that you can't always see, and it's really hard to predict. It's the danger of resonance.
Okay, so we've cushioned the pulse, right? But what happens if the system itself, the pipes, start to vibrate in sync with the pump? What if instead of being dampened, the shaking actually gets stronger? What if it gets amplified?
To get our heads around this, we have to talk about something called natural frequency. Basically, every single physical object, from a guitar string to a bridge to a long section of industrial pipe, has a frequency it just wants to vibrate at. If you give it a little tap, that's the frequency it's going to ring at. That's its natural frequency.
And here is where things get really dangerous. If the frequency of the pump's pulses, engineers call this the exciting frequency, if that frequency matches the natural frequency of the pipe, you get resonance. And when that happens, the vibrations don't just add up, they multiply. Every single pulse from the pump arrives at the absolute perfect moment to make the pipe's vibration bigger and bigger and bigger until it fails, often catastrophically. Now this is where the real genius of modern engineering comes into play. You can't just build one of these systems, cross your fingers, and hope for the best. Nope, you have to proactively design for stability. You have to find and prevent resonance before a single piece of pipe is ever even welded.
To do this, engineers use these incredibly sophisticated computer models. They run what's called a harmonic analysis, which is almost like giving the piping system a CT scan to map out every single one of its potential natural frequencies before it even exists. And they follow strict industry standards, like API 674, which is basically the official rulebook for designing these systems safely.
And all of this complex analysis, all these rules and calculations, it all comes down to one critical number. A number that can mean the difference between a safe, stable system and a total disaster just waiting to happen. And that number is 20%.
This is known as the 20% separation margin, and it is an absolutely non-negotiable golden rule in piping design. It means that the pipe's natural frequency has to be at least 20% different, either higher or lower, than the pump's frequency. This creates a vital safety buffer, a kind of no-go zone that keeps the system operating far away from that dangerous resonance region.
Let's look at how this plays out in the real world. At an oil transport station, an analysis found a ticking time bomb. The piping had a natural frequency of 2.81 hertz, but the pump was pulsing away at 5 hertz. That is way too close for comfort. The only way to fix it was to fundamentally change the pipe's natural frequency by making it a whole lot stiffer.
So how'd they do it? They installed these specialized heavy-duty supports. And as you can see from the diagram, these are not just simple little props. These are serious, oriented clamps designed to lock the pipe down, drastically increase its rigidity, and completely change the frequency at which it's even able to vibrate.
And the result was, well, it was astonishingly effective. After they installed the new supports, the pipe's natural frequency jumped from a dangerous 2.81 Hz all the way up to 28.03 Hz. Now, that is a huge, safe distance from the pump's 5 Hz frequency. The risk of resonance was completely eliminated, guaranteeing the system's long-term safety.
But the story doesn't just end with a perfect design. See, taming this beast isn't a one-and-done kind of fix. It requires a permanent, ongoing commitment to vigilance.
Because think about it, even the most brilliantly designed system can fail if you don't maintain it. Supports can come loose, foundations can settle, things change over time. That's why routine inspections are absolutely non-negotiable. At the end of the day, a system is only ever as strong and as safe as its supports.
And this kind of leaves us with one final thought. Our modern world absolutely relies on this powerful and, let's face it, inherently violent technology. Trillions of dollars of infrastructure, not to mention countless lives, depend on it operating safely. So the ultimate question isn't just about the engineering, it's about culture. How do we make sure that the human vigilance that's required to keep these systems safe is never, ever compromised?